The water cycle is an essential part of life on Earth. The rain that falls from our skies might be an annoyance on your summer holiday, but it is critical to ecosystems across our planet. However, there are places on Earth where the rain doesn't just nourish the land, it scars it. This is the result of something we call acid rain, a phenomenon born from the chemistry of the skies and from the hands of humanity. But where exactly does acid rain come from? What is our part in its formation, and how can we reduce it? We might think of our water as being perfectly neutral, but in actual fact, all of our rainwater is actually slightly acidic. This is perfectly natural and is due to the fact that water absorbs small amounts of carbon dioxide from the air and forms a weak acid called carbonic acid. Pure water at 25 degrees centigrade actually has a pH of 7, but rainwater usually has a pH of between 5 and 5.5 due to that small amount of CO2 it has encountered in the air. However, we're not talking about carbonic acid today, but something much stronger. Because of water's ability to dissolve atmospheric gases, it can produce much more acidic solutions if it encounters other pollutant gases in our atmosphere. And unfortunately, our modern lives have the ability to produce these gases in abundance. The two gases we will concern ourselves with are sulphur dioxide and nitrogen dioxide. Here they are here, SO2 and NO2. Put simply, these gases react with atmospheric water vapour and water droplets in clouds to produce sulphuric and nitric acid. Sulphur dioxide leads to the formation of sulphuric acid and nitrogen dioxide to the formation of nitric acid. We don't need the specific reactions for GCSE chemistry, and we can just write sulphur dioxide plus atmospheric water leads to sulphuric acid, and nitrogen oxides plus atmospheric water lead to nitric acid. I will make a more detailed video on these reactions because they are quite interesting, but they're certainly not required for your GCSE chemistry course. Now, these acids produced will, of course, be very dilute, but they will still typically have a pH of between 4 and 4.5. This wouldn't sting your eyes, but it's capable of killing plant life, harming fish, and damaging buildings. That said, the worst acid rain in recent times had a pH similar to that found in vinegar, and places such as the west coast of Scotland and the American Great Lakes share this unenviable title from the early 1980s. However, since these dark days, we've worked hard to reduce the amount of sulphur dioxide and nitrogen oxides in the air. But in order to do so, we have to understand where they come from. We'll start with NO2. To produce any compound, we need a source of each of the elements. And of course, both here are readily available in our atmosphere. I mean, after all, our air is 78% nitrogen and 21% oxygen. And the reaction itself is pretty straightforward. N2 plus 2O2 goes to 2NO2. However, it can also form nitrogen monoxide, and that forms in a similar way, but then reacts with the oxygen in the air to form NO2 all over again. So, because NO and NO2 can both lead to the formation of nitric oxide in our atmosphere, we tend to group these gases together and then say oxides of nitrogen at GCSE. And the only equation you need is this word equation. Nitrogen plus oxygen goes to nitrogen oxides. But if the air is chock full of oxygen and nitrogen, why are we being constantly suffocated with nitrogen oxides? Well, it turns out it's actually pretty hard to get the nitrogen and the oxygen to react. You need very high temperatures or pressures, or some very special enzymes. In the natural world, we only get very small amounts of nitrogen oxides, and these come from certain bacterial respiration reactions, volcanic activity, or lightning bolts. Unfortunately, the high temperatures and pressures found inside combustion engines, such as those on the cars passing behind me, provide excellent conditions for this reaction. In your exam, you might be expected to recall the following word equation and its associated conditions. So learn this bit carefully. By the way, when scientists talk about nitrogen oxides, they might use the term NOx, or more correctly, NOx. That little x represents the number 1 or 2, and so NOx can mean either NO or NO2. Make sure you're familiar with that term for your exams. What about sulphur dioxide? Well, the equation is very simple. Sulphur plus oxygen goes to sulphur dioxide. And in this case, we already know we have plenty of oxygen in the air. But where's that sulphur going to come from? Well, the short answer is you, and indeed every living thing. The biochemistry of all life that we know uses sulphur atoms within its enzymes and its protein structures. And this means that anything that is alive, or ever has been, will have some sulphur atoms within it. And these don't just vanish when that organism dies. If we burn the remains of any living thing, the sulphur atoms will react with the oxygen in the air and we will form sulphur dioxide. Burn a fossil fuel and you're burning ancient biomass. Burn wood, grass, or even animal dung and you're burning current biomass. Basically, if you burn it, you're adding some sulphur dioxide to the atmosphere. And then sulphur plus oxygen goes to sulphur dioxide, and the second half of that reaction, sulphur dioxide plus water, leads to sulfuric acid. Now, it's easy to think that this is just another depressing story about pollution. But here's the twist. This is actually a success story. Since the 1990s, both Europe and North America have cleaned up their acts considerably, such that the problem of acid rain for these areas has largely disappeared. So how was this done? Well, in a combination of ways. In cars, the addition of catalytic converters has massively reduced that NOx emission, and lower sulphur fuels, along with some extra additives in our engine fuels, has made that process considerably cleaner too. Larger factories and power stations must scrub their waste gases before releasing them. This basically means passing them through a large volume of water so that the nitrogen oxides and the sulphur dioxides dissolve out of those gases before they are released. Additionally, we're moving away from burning fuels at all. An increased production of green energy and electric vehicles have had a huge benefit over the last decade. So, has it worked? Well, yes, it has. In Europe, the average NOx levels from transport sectors have fallen by around 50% since 1990, and SO2 levels by over 80%. Forests and lakes have recovered in both Europe and North America. And you should be happy about this too for your own health, because NOx and SO2 can cause breathing problems for you too, as well as harming the environment. So, thanks to a joined up response, we're all breathing a little easier now. The job isn't done though. Some of the reductions in Europe and North America have come from heavy industry moving to other locations in the world. And in some places, such as China and India, industrial areas can still suffer from acid rain. It's an ongoing battle, but you may well be the generation that solves it. And this is the reason we need more scientists and engineers. Maybe some of you watching this video right now will go on to change the world for the better. I mean, that's certainly my hope, and it's actually the reason I make these videos in the first place. So, good luck with your studies, and I'll see you next time.